Hello everyone, welcome to this presentation. Take a moment to look at this image, three jars, each containing the same set of colorful balls but arranged in completely different ways. The first is highly ordered, second is more random, and the last shows the complete disorder, each step moving further away from order. This progression reflects a key law of nature. System naturally moves from order to disorder. Entropy is a concept that helps us understand this change. It explains how energy spreads, why processes are irreversible, and even why time seems to move forward in one direction. Today we'll explore this powerful idea and how it shapes the universe. Entropy is not just a concept, it is a story of how science came to understand the direction of nature itself. In the early 19th century, Carnot began exploring the heat engines, revealing that there are natural limits to how efficiently heat can be converted into work. Soon after, Joule showed that heat is not mysterious, it is simply another form of energy. The true breakthrough came when Clausius introduced the term entropy, established the idea that energy naturally spreads and system evolves towards disorder. This gave rise to the second law of thermodynamics, the principle that defines the direction of all the natural processes. Later, Boltzmann provided a deeper insight. Entropy is fundamentally about probability. System moves from order to disorder because disordered states are overwhelmingly more likely at the microscopic level. In the 20th century, the idea expanded beyond physics. Shannon redefined entropy as a measure of information and uncertainty, connecting it to the communication and computation. Today, entropy is everywhere, from the flow of heat to the evolution of universe. It explains why time has direction, why energy spreads, and why universe constantly moves towards greater complexity and probability. Entropy, in a sense, is the bridge between energy, probability, and time itself. We know from everyday experience that heat always flows from hotter body to a colder one, never the reverse on its own. To explain this natural direction of processes, scientists like Rudolf Clausius introduced the concept of entropy. Entropy can be understood as a measure of disorder or randomness in a system. In nature, systems naturally tend to move from more ordered state to more disordered one. For example, when heat flows from hot to cold, energy spreads out more uniformly, increasing randomness and reducing concentration. The spreading of energy reflects an increase in entropy. In an ideal reversible processes, this change happens in a perfectly controlled way, with no energy losses or internal disturbances. The system remains in equilibrium throughout, and the change in entropy is exactly balanced, meaning no extra disorder is produced. However, real processes are always irreversible. They occur over finite time and involve effects like friction, turbulence, and temperature differences. These factors create additional disorder within the system. Because of this, what is the perfect balance in an ideal case becomes an inequality in real life. Entropy increases not only due to the heat transfer but also due to this internal irreversibility. This is why the entropy of isolated system never decreases. It remains constant only in ideal reversible conditions, but in all real processes it increases as disorder continues to grow. Entropy therefore helps us clearly understand why heat flows in one direction and why natural processes move towards greater disorder. As we understand how entropy governs real processes, it naturally leads us to a deeper question: what does disorder truly mean at the microscopic level? Let's briefly understand the concept of microstates and macrostates. A macrostate describes the observable properties of the system such as temperature, pressure, and volume, while microstates represent the many possible microscopic arrangement of particles that correspond to that of the same macrostates. From the probability perspective, macrostates are not equally likely because they correspond to different numbers of microstates. A macrostate associated with a greater number of microstates has higher probability of occurrence. This naturally leads to the statistical definition of entropy. S is equal to Boltzmann constant times the log of omega. Here, omega represents the number of accessible microstates. This equation shows the entropy is directly related to probability. States with a higher multiplicity are more probable and therefore more stable in nature. In essence of entropy quantifies the number of ways a system can be internally arranged without changing its observable macroscopic properties. This explains why systems naturally evolve towards states of maximum entropy, as these states are statistically the most likely. Furthermore, entropy is closely related to the energy availability. While energy itself is conserved, its usability is not. Low entropy corresponds to energy that is concentrated and capable of performing work, whereas high entropy corresponds to energy that is dispersed and less useful. Thus, the entropy provides a measure of quality of energy, not its quantity, highlighting the inevitable degradation of usable energy in all natural processes. Let us step beyond equations and understand the deeper idea of entropy. At its core, entropy is not just a measure of disorder, but a fundamental principle describing how nature evolves. It tells us that all systems naturally tend to spread out, disperse, and reduce concentration. Energy, matter, and even information move towards states where they are more evenly distributed because such states are more probable. This idea becomes even more striking when we look at the atoms and nuclei. Inside an atom, especially nucleus, energy can exist in highly concentrated forms. However, such concentrated states are statistically less likely compared to the states where energy is spread among many particles. This is why powerful processes like nuclear reactions release enormous energy. In nuclear fission, a heavy nucleus splits into smaller nuclei, and energy that was once tightly bound becomes widely distributed among particles and radiation. This transition represents the shift from low probability concentrated states to high probability dispersed state. The same principle explains something as simple as heat flow. A hot object has energy concentrated at atomic level where the cold object has it more spread out. When they interact, energy flows from hot to cold, not just because temperature difference, but because such a distribution maximizes the number of accessible microstates. So whether we observe atomic reaction or everyday thermal processes, the underlying rule remains the same. Systems evolve from less probable concentrated state to more probable distributed states. In this way, entropy reveals a profound truth about the universe. Nature always moves towards greater probability, greater spreading, and greater balance. Having seen how entropy drives physical processes, we can now explore its most profound consequence, its connection to time and evolution of universe. Entropy is often introduced as a simple measure of disorder, but it is far more than that. It quietly governs the universe's story, giving the time its direction and reality its irreversible flow. At its core, entropy is about probability. Any system can exist in many microscopic arrangements, but only a few appear ordered to us. Most are disordered, not by preference, but because they are more likely. Systems naturally evolve towards these more probable states, which is why entropy increases. This leads directly to the arrow of time. While the fundamental laws of physics are largely reversible, our experience is not. A shattered glass does not reassemble and heat flow from hot to cold. This asymmetry arises because the universe moves from lower to higher entropy. In this sense, time is not just what clock measures. It is the direction in which entropy increases. The past corresponds to low entropy and the future corresponds to high, where energy and matter becomes more dispersed and explore more possibilities. This universe itself begins in extremely low entropy state. From this, all structures like galaxies, stars, planets, and even life has emerged. This does not contradict entropy. Local order can form, but only by increasing the total entropy of the surroundings. Life and complexity are not exceptions, they are natural outcomes of these processes. At the same time, chaos theory reveals that even deterministic systems can evolve unpredictability. Tiny differences in the initial condition can lead to vastly different outcomes, limiting long-term predictions. Order doesn't simply decay into randomness, it often transforms into complex sensitive patterns. Ultimately, entropy and time are inseparable. Entropy gives time its direction, its before and after. Without it, time would have no arrow, no history, and no evolution. But simply, time is a manifestation of universe's irreversible progression towards more probable states, and everything within it exists as a part of ongoing transition from ordered to equilibrium. In conclusion, entropy is the force that gives direction to the time and drives all natural processes towards greater disorder. While energy is conserved, its ability to do work decreases over time. Yet, even as disorder increases, nature still creates order in remarkable ways. Entropy is not just about disorder, it is about understanding the flow and evolution of universe. Thank you for your kind attention.